So I never really started out to be an inventor. If anything, I was taking a path of pretty much computer science about 25 years ago. But I decided that computers were actually kind of boring. This will be in a landfill in 3 years. So I started thinking about what I was going to do next. And it took me into the field of genetic engineering. In some ways, it's a lot like computer science. Instead of programming silicon, you're programming a living cell to do something interesting. It was a pretty new field back then. I was actually working at the intersection of computing and biology, called bioinformatics. Back then, DNA sequencing was kind of new. Remember when the Human Genome Project was first launched? $3 billion effort to read the code that makes a human being. A very ambitious project, by the way, because we hadn't even read the code of a single bacterium at the time. We'd only read the code of some small viruses. But as genetic sequence started to flow into databases, we needed computers to understand this work. And I ended up shifting most of my work into the interpretation of genetic code. It was actually a really exciting time. There were so few people doing this type of analysis on code that I could pretty much write my own ticket. And I was hired away from my PhD program by the biggest biotech company in the world at the time to work in their bioinformatics groups. And it was an eye-opening experience, because one day I'm a poor grad student, and the next day I'm reporting to a vice president that is fantastically wealthy in one of the most powerful companies in the world. This company spent more on research and development than my entire country, Canada, did. So it was quite an education. Now, if you know anything about genetics, most of it is paid for. Most of the grants get written for cancer, because cancer is a genetic disease. It is essentially the corruption of a genetic program in your body, leading to cells that keep growing when they're not supposed to be growing, and ultimately causing an infection in your body that crashes the network if it's a bad enough cancer. So I really hate cancer. I learned a lot about this disease, both from a biological perspective, because I'm trained in microbiology and cell biology, but I also learned about it from a genetic perspective. And there are literally tens of thousands of corruptions in the genetic code in a typical cancer cell versus a normal cell. Far more than most people could keep in their mind and interpret. And I also learned about it from a business perspective, because cancer is big business. Right now, we sell about $100 billion worth of cancer drugs per year in this country. So I also got really upset with the way we treat cancer. There's a fantastic book called The Emperor of All Maladies, which is kind of a history of cancer. It's been turned into a TV show, a special documentary. And it is stunning at how barbaric some of the treatments were, surgically, and in some cases radiation, but certainly chemotherapy. Chemotherapies are actually derivatives of chemical warfare agents that were used in World War I. And frankly, they're not very good. They target all fast-growing cells. It's kind of, you've got a cell you want to kill, carpet bomb everything. You have a terrorist in the city, nuke it. That'll get rid of the terrorist. The problem is we have lots of normal cells that grow as well. And so you get all this collateral damage. So carpet bombing doesn't work very well. And today we have much better drugs much more targeted, but they're so expensive that a lot of people simply can't afford them. In 2013, every single cancer drug that was brought to market cost more than $100,000 per year for treatment. And now often you need multiple drugs. And of course, that's just the drugs. That's not the surgery and the hospitalization. So basically, if you get cancer, you're bankrupt. Even the co-pays these days can run $30,000 or $40,000 just for the drugs. So, and I knew this because I worked inside the drug companies. There's no pricing model, no economic model that makes sense for drugs today. And this really upset me. And then there's something worse. Angelina Jolie famously removed her breast tissue because she knew she had a high likelihood of getting cancer. It was worth the risk simply to lop off the tissue before the cancer appeared. We've lost innovators that are rich and famous and plugged into the entire world to cancer. Doesn't matter how rich you are, you will die. We've recently lost Bowie and Rickman. The sad truth is, even with all the investment we've put into cancer since the war on cancer was declared in 1972 with Nixon, and most recently with Obama and Biden, cancer drugs don't work reliably for most of us. If you look at the 20-year data for survival, 5-year survival in cancer, it's incremental. 5% here, 8% there, 11%. We almost never see cures. So when I see something that's overpriced, isn't really working for most people, even wealthy people like us, and isn't changing, I just see an area ripe for disruption. And I love disruption. I'm not an inventor so much as a troublemaker. Over 10 years ago, someone dropped a paper on my desk that got me excited. It basically described the use of viruses as cancer treatments. Turns out that viruses, as you know, infect cells. Catch a cold, it's infecting cells in your nose and respiratory system. Gets into the cell, starts to grow, causes a lot of damage, your immune system typically mops up, no big deal. Well, it turns out that some viruses only infect cancer cells. And that's really cool because it kills the cancer cell, but also releases a lot more virus to go on and infect other cancer cells. These cancer-fighting viruses fascinated me, and it turns out almost every human virus that we've studied, polio, measles, adenovirus, actually has anti-cancer ability. And people have been investigating how to use viruses as drugs for 40 or 50 years. And it kind of pops up every now and then. There's a bubble of research and it goes away, and it pops up again. And it turns out so many viruses do this, the whole field is fragmented. But I got really interested because I'm a genetic engineer. And I know that the code to make a virus, the actual DNA code or RNA code to make a virus, is really small, it's really short, and it's really easy to engineer. So coming from a software perspective, it's like writing a short program, an app, not an operating system. So I started working to make synthetic viruses. And I'm quite fortunate. I work for a global design company now, Autodesk. We make software for designing really big, complex things like buildings. Every skyscraper in the world basically uses our software. Automobiles, most products you have in your pocket, and pretty much all the special effects you see in movies. We make really good complex software for seeing things that don't exist yet and for modeling them before they exist so you can understand them and test them before you spend billions making it. But we didn't have a bio-nano division until I came along with some of my colleagues. So I've been working with Autodesk to build essentially systems to 3D print viruses. And this is a 3D printed virus particle. It's not a real virus. It's a model. But we've been developing software tools that allow us to engineer viruses pretty much at the molecular level. I'm sorry these movies aren't playing on this particular machine. But we can get atomic precision control over the engineering of virus particles now, all designed on computer. We can actually print the genome of these viruses using companies like Gen9. You may never have heard of these companies before, but they take all of the work out of genetic engineering because now you can simply print the genome, the DNA of small things like viruses at a relatively low cost. We started prototyping robotic lab systems, so you don't even have to go into the lab to do this work. The entire process, design, build, and boot up and test of the virus, all done digitally. And a couple of years ago, we made our first synthetic virus. This isn't a cancer-fighting virus. It's basically an antibiotic. It's a virus that kills E. coli bacteria. Wherever you see a spot on this growth plate is where a synthetic virus didn't start from nature. It started from a file on my computer, was designed, printed, and ultimately booted up in a cell to kill cells, in this case E. coli cells. Total cost, $1,000 2 years ago. Total time, about 2 weeks, start to finish. With this type of a system, you can actually engineer specific cancer medicine. Make it for one person and one cancer at a time. That's a disruption. The really exciting part about that is if you can make a medicine for one person, you lop off, you throw away the most time-consuming and expensive part of bringing a medicine to market, which is phased clinical trials. Drugs are actually really cheap to make. Ask anyone with a meth lab. Making a legal drug, that's hard, because now you have to prove to people that it works for whatever you're making it for, and you have to show that it's safe, potentially for millions of people. You don't have that problem if you're making it for one person that's already been pre-screened for the drug development process. That's pretty radical. I love the fact that we're essentially giving cancer cells a cold. This doesn't have to be a really extreme therapy. You can kind of ratchet it up slowly, kind of annoy the cancer cells to death. I'm really excited to say that my team has moved beyond killing bacteria, and now we're working with veterinarians to build the first cancer-fighting virus that's synthetic for a dog. This is really exciting. It's the forefront. Now, we're not actually worried about curing that dog. I'm worried about making this process, which is already extremely cheap, and then starting to be able to connect lots of researchers and doctors and innovators to the process. It's like 3D printing. Once you have the software and the printer, you might make a little toy for your child, you might make a part for a spacecraft. It's a platform technology. The process is actually really simple too. End to end, you start with a single dog. You profile their individual cancer. You sequence that cancer. That's the beautiful thing about DNA sequencing. It is cheap today. You learn so much about that cancer cell. That goes into the design software. Then you print the genome, boot the virus, purify it, test it, and now you're pretty much ready to go back into the clinic to treat. The results of these types of cancer-fighting virus trials inserted in between surgical removal of the tumor and standard chemotherapy is pretty remarkable. And this whole process, because it's digital, just gets faster and cheaper every time you use it. It gets smarter. We already have a lot of tools that help with this process. Autodesk, I'm really proud to say, we make some of the most complex software tools in the world that make really hard jobs easier. Last year, we made the decision to give all the software away to students and to faculty. So if you're interested in trying out any of these tools for any reason, buildings, cars, maybe even drugs, take a look at students.autodesk.com. You can get $200,000 worth of software essentially for free now. But the thing that excites me about this is we're really talking about making an entirely new drug development pipeline. One that can move very quickly, one that can be very effective, one that can be very safe, and potentially can make medicines that are affordable to everyone. I never want to actually sell a drug to a human being. I want to give them away for free. And if that sounds a little weird to you in terms of business model, remember just about everything you use today in the digital world, Facebook, Twitter, Google, most of it's free to you. We have different business models that support it. You just have to get a little creative. I never want to make a penny off of your suffering or your disease. Frankly, I think that's just wrong. If you're sick, if you're dying, and you can't get the drug that could save your life because you don't have enough money, if I'm the drug maker, I don't feel good at night. I don't sleep well. This is a really easy area to get into. You're advanced. We teach this to high school kids now. There's a book you can buy for 35 bucks by O'Reilly, the computer software publisher, that describes how to get started in this field. More than that, we've been training students for over a decade in a program that started at MIT called iGEM, International Genetically Engineered Machines. An engineer named the program, but it has trained over 25,000 students in this type of technology. They're not all working on viruses. Some of them are reprogramming cells to make medicines or foods or related technologies. Once you can learn how to write DNA, you can start to affect every living thing on this planet. It's just a matter of choosing what you want to go write some code to. When people say that, oh, genetic engineering, isn't it dangerous? It's like, no, it's the coolest programming industry in the world. Programming carbon-based life, rather than silicon, is the future. You need computers to do it, to augment your skills, to connect and create collaborations to do it well. But trust me, it's so much fun once you get started. And this is a living world. It makes a real difference being able to shape it to our needs. Anyway, thank you very much for your attention. I'm sorry to keep you away from the food.